right, hello adventurers, and welcome to the last video on floor 9.5. This is exciting. We are getting close to the end here now, which does make me sad. In our first video on this floor, we were able to measure the lean via the balance factor function and also the is balanced function. In the second video, we created rotations that would repair an imbalanced tree. And at this point, our self-test phases 1 through 4 are green. Today is one more small function, rebalanceAt. The decision of which rotation to apply, and then the real point of this whole half floor, you're going to get to compare your plane tree to a standard set, and you learn that you do not hand build a self-balancing tree. You reach for the one the library itself has already balanced. This is the compare and don't reinvent type payoff. The code today is tiny. The benchmark and the closing argument are the lesson. Today also has a no-code board segment on Notepad++, which deals with something called the zig-zag, why one rotation isn't always a balancer. And that sets up why the standard set has to work as hard as it does. Okay. Now, what we can do at this point, if we build our executable just to show where we're at, let's do that just to kind of get our floor set up for ourselves. Okay. Okay, so you see we're still at the point right here where we have an issue with our balancing root. Our right and left heavy sticks both rebalance. Order kept, fail. Rebalance must rotate left when our balance factor is less than -1 there, and right when it is greater than 1. Okay, so we can measure our lean, and we can rotate to fix one. The only thing missing is the decision. Given a lopsided node, which way do we rotate? That's going to be our phase 5, which is still red. It's our last stub. And it's just 3 lines of code in order to fix it, which is pretty exciting there. Okay. Now, let's quit out of this. Perfect. And then let's go ahead and get to our rebalanceAt function, which I was already here in our hero/BST header file. We're going to say if n is equivalent to null pointer, we'll say return n. We'll say const int bf for balance factor equals balance factor of n. We'll then say if our balance factor is greater than 1, we will return rotate right at n. So this is our left heavy scenario. Say if balance factor is less than -1, return rotate left of n. This, of course, is our right heavy scenario. Okay. And then otherwise we return n. So this is the whole decision a self-balancing tree makes, distilled to one node. We measure the balance factor. That's the first video's function. If it's greater than 1, the node is left heavy, so we rotate right to pull weight off the left. If it's less than -1, it's right heavy, so we rotate left. Otherwise, it's already balanced, therefore you leave it. That's it. Measure, pick the matching rotation, balance root. This public method just calls this on the root. So let's go ahead and let's build it. Exciting, isn't it? Boom. Look at that, man. I love to see all green, don't you? So all the phases are good. Phase 5 confirms balance root rebalances a right heavy stick and a left heavy one. It picked the correct rotation in each direction and kept the order both times. You now have by hand every ingredient of a self-balancing tree: the measure, the move, and the decision. So now let's use them on McCown's actual catalog. So let's say balance. There we go. So see McCown's catalog, 15 names, height 6, root balance factor -3. It's not balanced. It is lopsided. So it's still lopsided. It's a height of 6, factor of -3. But why? We have balanced root now. Because balanced root fixes just one node, which is the root. If a tree leans for 6 levels, it needs the fix applied at every node over and over every time it changes. Doing that by hand forever is a losing game, and that's the lesson. That's once again why we talked about the standard libraries set. So let's benchmark our balance. So you see same sort of input, you're playing binary balanced binary search tree, sorry. Versus standard set, 1,000 iterations. So you can see here as we scale up our plane algorithm versus our standard set at differing heights, and then the time it takes for us to find. Okay, so same data, same order, inserted in sorted order. Our plane BST degenerated into a stick of height n-1. The lookup time goes back to O of n. Yikes. Right? Standard set saw the identical input and stayed shallow. It is a balanced tree, what we call a red-black tree, that rotates on every insert to hold its height near log base 2 of n. You do not handwrite that balancing. You should reach for the standard library set or map. That is going to be what we deal with in the next floor, the Hall of Names. Okay? So you can see how ours kind of blows up there later on. Okay. So let's go ahead and move to the board for our last part here today. Okay. So I just a little zigzag here. We have 1 at the top, 3 to its right, and 2 as 3's left child. Here's why standard library set has to work harder than our balanced root, and why we stopped where we did. This little tree, 1, then 3 to its right, then 2 tucked under 3 on the left, is right heavy at the root. Our rule says right heavy, rotate left. Try it. So if we do that, okay, so 3 comes up, 1 goes left, and now 2 is hanging off in a way that's still crooked. 1 rotation just ends up moving the lean around, okay? So if we did that, we would have a case where we'd be up here. And so that's obviously not going to work well. My bad, I need to fix this right here. So 3 becomes the new root, 1 becomes 3's left child, and 2 becomes the right child of 1. So it ends up looking like this. So we kind of end up having this same sort of lean right here. And here I can kind of make them be a little bit like that. So you can kind of see we end up with the same type of problem there. Okay, so that's obviously not good. This is the zigzag case, and it needs 2 rotations. We first rotate the child to turn the zigzag into a straight line. Then we rotate the root. A real AVL tree detects this and does the double rotation automatically. A red-black tree, which would be in the standard library set, keeps balance a slightly different way with node colors and its own rules, but the idea is the same. A little bookkeeping on every insert so the tree never leans. That is the code we're choosing not to write. Not because we can't, because it's a lot of careful, already solved work, and the people who wrote your standard library got it right and tested it to death. The professional move isn't to re-implement standards set, it's to know what it's doing under the hood, which you now do, and then Trust it. Okay, now I feel like I'd be remiss if I didn't show you what the two rotations should be. So we did a rotate left here. We ended up still having this hanging problem. But if we did have a case where this was our tree here, where we had the right and then the left scenario, what we would want to do, first of all, because this has a right-left imbalance, what we call an RL imbalance. So what we would want to do first, we should do a right rotation at 3, because doing that would lead it to where we had 1, and then we'd have, I'm even going to draw the little deals out here, 2, 3. So the first step is to get it into a straight line where it's all in the right order. And then we do a left rotation at 1, which would then shift it to where we had 1 right here. Sorry for being so slow here. 2, 3, as such. That would be the correct way to solve that problem there. Okay, so let's just sit here and step back and think about this whole work we've done with the trees section. In floor 8, we built a general tree. In floor 9, you made it search itself in log in and watched it decay into a stick. Floor 9.5, which is this floor, you learn to see that decay, to repair it with a rotation that never disturbs the order, and then to recognize that keeping a tree balanced forever is exactly the kind of solved, fiddly work that you should hand to a library. That recognition is a real engineering skill. Not can I build it, but should I when standard set already did. And that's the door we're going to walk through next. You have built 5-pointer structures with your own hands: a chain, a stack, a queue, a tree, and a BST. Starting next floor, you stop building them and start using one. The Hall of Names, where every key has its value beside it. Found not by descending a tree you maintain, but by simply asking a standard set or a standard map. Balanced red-black trees, the very thing you just benchmarked, handed to you finished. Now, I would just make sure read the floors page, check for understanding, make sure you're ready to go. McCown straightens the last branch, and for once, it holds. The bard has already learned your next verse, and here soon, it'll be time to see you in the Hall of Names. Now, another thing, too, here, real quick, a red-black tree, just to make sure you're clear on that, is a self-balancing binary search tree where each node is colored red or black. The coloring rules prevent the tree from becoming too unbalanced, so searching, inserting, and deleting all take O of log n time. After changes, the tree uses that recoloring scheme and rotations to restore balance to it. Anyways, I hope this was helpful, and I'll see you on floor 10. Bye-bye now.